Welcome and thank you for joining. Let's take a look at another example where we have to find the intersection made between three planes. So as you can see here, we are given the scalar equations of three planes, and we're going to start off by numbering them. You can choose letters if you wish, A, B, C, and I choose to number them 1 to 3. It's the same thing, matter of preference. So the next thing that I want to do before starting solving the system of three equations is identify the normals to each plane. Now remember that the scalar form of the equation of the plane is ax plus by plus cz plus d equals 0. And when equations are given this in scalar form, then we can identify the normals or the perpendicular to the plane by simply looking at the coefficients of x, y, and z terms. So a, b, and c will be the coordinates x, y, and z of the normal to a plane. Now recall that if two planes have equal normals or normals that are scalar multiples of each other, they're either parallel to each other, which means they won't make any intersection at all, or they are coincident planes, which means that all the points will be common points on each plane. So they will have an infinite number of common points. Now, we're going to start off by identifying each normal because knowing the normal to each plane can give us information about how the planes are positioned against each other, and therefore it can give us an idea of what kind of intersection we have to look for. As you can see here, the normal to the first plane will be 2, -1, +1. The normal to the second plane is 3, -5, and 4. And the normal to the last plane will have the coordinates 3, 2, and -1. As you can see, these normals are not equal to each other, and you see that you can tell that they're not scalar multiples of each other either. So that tells us that the three planes will have different normals, and thus they would either intersect at a point or along a line. So to solve these kind of questions or to find the intersections made between three planes, we basically follow the same steps. However, the outcome of each step may be slightly different, and that will help us divert our process a little bit. So choose a different process for every system of equations. But there are two steps that never change. Step number 1 is create two systems of two equations by pairing the equations 1, 2, and 3. Now, the order in which we do that doesn't matter. And step number 2, we have to eliminate the same variable from each system. We have to make a decision of which variable is easier to eliminate, but then we have to eliminate the exact same variable from the first and second system. So I'm going to start off by creating the first system of equations. So I decide to pair up equations 1 and 3. So 2x minus y plus z equals 1. And equation 3 is 3x plus 2y minus z equals 0. You can tell that I chose equations 1 and 3 to sit together because I see that the z coordinate is easier to eliminate here because they have opposite coefficients. So here goes 1 and 3. And the second set will be made from equations 2 and 3. So again, this is the only other choice I have. So 3x minus 5y plus 4z equals 3. And 3x plus 2y minus z equals 0. So this is the other choice I have to pair up the equations, so equations 2 and 3. And we could have also combined 1 and 2, but we would have to do the same amount of work. I chose 2 and 3 because the signs are already opposite, but it shouldn't really matter. So let's number these equations so we know which ones we've paired together. So these are the equations 2 and 3. So in the next step, we have to eliminate the same variable from each system. And I've already made up my mind which variable to eliminate from the moment I was trying to make a decision of how to pair up the equations. So I will eliminate the variable z from the first system, and that will give us So this can be done by addition in this case, and that is because the signs are opposite. And that will give us 3x plus 2x, 5x. Negative y plus 2y is 1y. Z plus negative z is equal to 0z. Obviously, we don't have to write this, but for the purpose of explaining things, I'm just writing it down. And that will create us 5x plus y equals 1. For the next set of equations, we will have to make some modifications to the second equation, so we'll be able to eliminate the variable z. So that means we are multiplying by 4 the second equation, so the system has become 3x minus 5y plus 4z equals 3, and 12x plus 8y minus 4z equals 0. So we'll add the two equations, and that will give 3 plus 12, 15x. Negative 5 plus 8y is 3y. The z term will simplify to 0z, and 3 plus 0 is 3. So as you can see, we have a common factor of 3 to all terms. We'll simplify as much as we can. So we'll divide by 3, and that will create the equation 5x plus 1y equals 1. So we will number the equations that we obtained with numbers 4 and 5, or we can letter them just so that we can distinguish these new equations that we created from the equations that we used in the previous step. So this time I'm going to call them the equations A and B. So as you can see here, equations A and B ended up being the exact same equation. So if we put them together, 5x plus y equals 1. So that would be our equation B. Then if you try to solve this system of equations, which will be the natural way to think of in this process, because we are trying to discover what the values of the variables x, y, and z are. So if we were to eliminate any of the variables, we will end up with 0x plus 0y equals 0. So what that means is that any x or y value can satisfy this equation. So it doesn't really matter what the x or the y value would be. So this will be true for any real value of x, for any real value of y. So in this case, we draw the conclusion that there will be an infinite number of solutions or infinite number of common points, because we can find an infinite number of values of x and y that satisfy the equation of common points. So now let's think for a second. Now, infinite number of common points, so if three planes intersect, will lie either on a common line of intersection, because a line hosts or has an infinite number of points, or it would lie on a common plane, because planes also host an infinite number of common points. Now, from the analysis that we did before, we noticed that the normals were all different, so there is no chance that these three planes will have an infinite number of common points that lie on a plane. So in this case, then, we'll say that the common points will lie along a line. So now we know what we're looking for, and this is what I was talking about when I said the first two steps are exactly the same. And after this, we have to use logical reasoning to understand what type of solution we're looking for. So, how do we find the common line of intersection? Now, remember that, and I wanted to try to imagine a line in 3D. So, or even simply actually, so try to imagine a line in 2D. That's easier for us to kind of imagine because we work with it for a longer time. So if we have a line in 2D, remember lines extend at for any real number. So the x values will extend to infinity, and so do the y values, which means that for any value of x, for any input value of x, we can find a value of y. This is the reason why we say that for a line in 2D, the domain is any real number x, and the range is any real number y. So when it comes to lines in 3D, we say about the same thing. Because lines extend infinitely at both ends, if we have a line in 3D, doesn't matter where the line is located, then the domain for the x values will be any real number x, because the line continues this way and continues in the negative values of x. Domain for y can be any real number y, because the line will continue down this way to meet the negative y values and up this way to have all the positive y values. And same can be told for the z values. So in this case, because we have an infinite number of common points, instead of saying let y be a specific number and give it a real value, we are going to say that using the equation 5x plus y equals 1, which is a relationship we discovered between x and y by using the equations of these three planes, which means that this equation must be true for the system of equations that we're trying to solve. We're going to say that we're going to let y be a number. And we're not going to give a specific value because there's an infinite number of them, but we're going to give it a letter to describe it. For example, we're going to let y equal some number t, where t is a real number. So if y equals t, so if y equals a number, imagine substituting a real number. How do you find x? So you isolate x and express x in terms of the rest of the numbers. Now, because we don't have a real number, but we have a letter that represents a real number, then we're going to say that 5x plus t must equal 1, which will make x equal to 1 minus t divided by 5. So in a proper form then, or should I say in parametric form, x then will be equal to 1 over 5 minus 1 over 5t. So far we have disclosed an expression for the values of y, one for the values of x, and it's time that we find the values of z. So to find the values of z, we can use either equation given in the system, and always make a wise choice. Choose the equation that gives you less work with all these other terms to simplify. And I would choose equations 1 here because z is already positive. And so for z in terms of whichever values of y or x can be. So if y is some number t and x equals some number 1/5 minus 1/5 of t, that means that the value of z from the equation 2x minus y plus z equals 1 will be 2 times 1 over 5 minus 1 over 5t minus y is equal to t plus z equals 1 will give us the value of z equal to, let's take a look at what we obtained. So we have 2 over 5 minus 2 over 5t minus t, and then plus z equals 1. So continue isolating. So I will leave z on the left side, and I will take the rest of the term to the other side. So 2 over 5 will join number 1, so 1 minus 2 over 5. And these two terms combined together will come to the other side as well. So t plus 2 over 5t. We can choose to simplify them while they're on the left side. It's the same thing. So now let's simplify so we can figure out what t is. Obviously, you can use a calculator, but always try to use mental math whenever given an opportunity. So number 1 is 5 over 5 minus 2 over 5. That makes 3 over 5. And here we have t plus 2 over 5t. So that means 5t over 5 plus 2t over 5. That makes 7 over 5t. So with this, we have derived an equation for the variable z as well. So as you can see, we couldn't find a single point because obviously they do not intersect at a single point. They would have if we would have been able to find or to solve the equation for x or y and then get a real number, but they don't, right? So we gave y any value t. We found the value of x based on whatever values of y would be, and then the values of z. If you look at all these x, y, and z values we obtained, you probably recognize that these are actually the parametric equations of all the points that lie along the same line. So if we want to express the equation of the common line in vector form, and I will be rewriting all these equations one more time together and put them in order. So x is equal to 1 over 5 minus 1 over 5t. Y equals, as you can see for y, we do not have a constant, so we're going to call that 0 plus 1t. And z equals 3 over 5 plus 7 over 5t. So therefore, we're going to say that the equation of the line of intersection will be made of a bunch of points with coordinates x, y, and z such that the position vector will be made of the constants 1 over 5, and then 0, and then 3 over 5, and then plus t. And these numbers here that are the coefficients of t will make the coordinates of the direction vector of this line. So we have t, negative 1 over 5, positive 1, and 7 over 5. Close the brackets. Now, if you look at this equation, you see that you have the coordinates of a starting point, or the position vector, and the direction vector, which is in fraction form. Now, one convenience that we're always offered is to convert the direction vector coordinates into numbers, into integrals, and we can easily do this by multiplying by the lowest common denominator of all. In this case, the lowest common denominator is 5. Now, remember, though, that the coordinates of the starting point, so the 1 over 5, 0, and 3 over 5, will not change. But we can easily change the coordinates of the direction vector into, in this case, negative 1, positive 5, and positive 7 by simply multiplying by 5 every single term. Now remember that when it comes to direction vector, all we worry about, or what we need to get from it, is the direction. It doesn't really matter how long the direction vector is, and that's why we have this freedom. However, we cannot change the coordinates of a point. And the reason why is because when we find the equation of a line, yes, we do follow the direction vector, which can be this long, or it can be this long, so different coordinates. But when it comes to the point where we start from, it has to be on the line. And we do not want to mess up with that. We don't want to make it bigger or smaller, because that will take us somewhere else, like not on the line, but somewhere else in 3D. And that won't represent the line that we are talking about. So it would be another line that may be parallel to this, but it starts at a different point. So this doesn't change, but we can modify the direction vector at all times. Now, one of the questions that I get asked very often is, let's take a look at how we found out the equation of a line. So we let y equal t. What if we decided to let x equal to t and then solve for the rest of the variables? So express the rest of the variables based on the fact that x is some number t. I encourage you to try this method. And what you will notice is that if you let x equals t instead of y, you will still end up with the same direction vector, but a different point. Because the way that you would read the line in this case is not, for example, from this particular point that we choose in here and following a direction vector as long as we want it, but we're going to start from a different point that we decided or determined based on x first. So it will be still the same line, but with a different initial point. So if we decided to let x equal t. The same can be said if we change the order in which we paired up the equations to make the system. So what I'm trying to say here is that the order in which we pair up the equations to make the two systems doesn't matter. So it will slightly change the way your common line of intersection look like. And the only thing that will change is the starting point. But the direction vector will be the same if we choose different pairs in here. And the direction vector will be the same if you chose to let x be equal to t or z be equal to t if you were to have z in these two new equations that you formed. So I hope this made sense. And if you have more questions, please ask them in class or email me so that we can clarify this. This is a very interesting concept to discuss and learn and study, but it can be a little bit abstract. But it's not impossible to learn, and it is actually quite fun once we get a grasp of it. Well, thank you for learning with me, and bye for now. I hope your day is wonderful.